Okay, I'm going to talk to you a little bit about the classification and representation of matter. But first, before we go into the classifications and representations, let's talk about the periodic table because that's kind of our foundation for any type of matter. It's actually an organized table of the elements that make up matter. Okay, and so all matter is made up of elements. And so it's good to know what are our possible components. And so from the periodic table, you get that. Okay. Now, a lot of periodic tables like this one have just symbols that represent the different elements. And so element symbols are always going to be either one capital letter or a capital letter followed by a lowercase letter. And some of those tie in kind of directly to the element name. Some of them actually are related to their Latin name. So some of them seem pretty obvious and others don't. That's just something you have to get used to. You can always have a list of the element symbols and element names kind of on hand as you need them. So a lot of periodic tables don't have element names on there just because some of them are kind of long and it has to be really small text for this table. And so a lot of times you just have an element symbol on there. So you need to be able to convert that then to a name to then apply it to things. Now there's also numbers on there. I don't want to focus on that right now. I just want to focus on kind of some basics of this organized table of elements, okay? First, the groups and the periods, okay? And so that's just a basic way to kind of refer to the layout of the periodic table and specify different areas of the periodic table. So groups, or we can also call those families, those are the vertical columns, okay? So up and down on the periodic table, okay? And so those are numbered, like on here, it's numbered with the Roman numeral 1A above that first column, and then 2A over the second column, and so on. Those are the different groups of the periodic table. Now, sometimes it's of interest to go a little more in depth, name those groups and so on. I don't want to deal with that right now. We're just looking at the basic layout and terminology kind of associated with that. And so if we're talking about groups, just remember it's the vertical columns in the periodic table. And the reason they're kind of clustered that way, or certain elements are in a specific group or family, is because chemically they behave similarly. Okay. And then periods are rows. And so the horizontal portions. Okay. And those elements that are within the same row don't necessarily behave chemically the same or similar. They just have the same number of shells of electrons. And so if you get more in depth into the electronic structure of atoms, that can be of interest or of importance. And so that's why there's this organization of the periodic table. Now, another way we can kind of simply break down the periodic table is to talk about metals and non-metals. Metals are, at least on this periodic table, kind of shaded in all different shades of blue. Now, they have sectioned it out into main group metals, transition metals, and intertransition metals. That's getting a little deeper in than I really want to right now, but at least you should realize that it's all the stuff kind of to the left-hand side of the periodic table are metals, with the exception of hydrogen. Notice that hydrogen is up there at the upper left, whereas that's just color-coded yellow because it's a non-metal. So it's placed there because it can behave like those group 1 elements, or most of the time that's what it behaves like. But with respect to being classified as metal, non-metal, their characteristics, it behaves more like the stuff at the right-hand side. Okay, so that's kind of the one oddball. whereas the things color-coded in yellow, those are non-metals, okay? And so we kind of have this stair-step line on the periodic table, okay? And so usually that's bold on there. And so that's separating your metals and your non-metals. Now on this, it actually does tell you about metalloids. In the metalloids, they've got color-coded green here, and so those are things that are generally really close to that stair-step line. Those are things that have characteristics similar to metals and non-metals. So to both, it's not really easy to just say it's one or the other, okay? But things that are classified as metals, things that are kind of to the left of that stair-step line, those are things that not only like what we typically think of metals are like shiny, they're bendable, or more scientific term, malleable. They also conduct electricity. Most people know that, right? We use metal for wires. They also conduct heat really well. Whereas the non-metals, the things that are kind of on the right side or above that stair-step line, those have kind of opposite characteristics. They're very different. So instead of being shiny, they're very dull in appearance. And instead of being bendable, if you tried to bend a sample of a non-metal, it would just break. It's very brittle. And they don't conduct electricity or heat. Whereas the metalloids, those kind of on that stair-step line, those have some characteristics like metals and some like non-metals. It just depends on which metalloid you're talking about. Now, if you're just going into kind of basics of chemistry, you usually ignore the fact that there are metalloids or semi-metals, and you usually just will separate it out. And so since like boron and silicon on that table are above the stair-step line, we'll usually just treat them as non-metals. And it's good enough for general purposes, okay? But if you went deeper in, you would have to realize that there is a reason that there's that extra classification, okay? But for the basics of chemistry, usually being able to distinguish at least these are metals, these are non-metals, that's good enough. And it helps us then understand compounds a little bit better. So when we start combining these elements into compounds, how they do that is going to be determined based on, is it metals interacting, is it non-metals interacting, or is it metals interacting with non-metals? Now, so that's kind of just our foundation of matter, or the elements, because everything that is matter is made up of elements. Now, whether or not it's one element or two elements or whatever, depends on what matter, what you actually have, okay? And so let's talk about the different classifications of matter. And I guess it might be good to start off with, well, what is matter other than things that are made up of elements, okay? Well, matter by definition is anything that occupies space and has mass, okay? And when we say occupies space, that would be something that has volume, okay? So basically matter is anything that has mass and volume, okay? And to help us better kind of study matter, we like to put it into different classifications. So we break it down and say, okay, we can have some matter that behaves this way, and we cluster it into one category. And then we could even break that down further. But then you can focus on studying kind of smaller groupings of things instead of everything in the world at once, okay, or everything in the universe, I should say, at once. So for matter, one major classification is pure substances. Okay, so pure substances are things that have a constant composition throughout. And so if I take that pure substance and I take smaller samples from it, it's the same stuff all the way throughout. And no matter how small of a sample I take, if I go down to the smallest unit of that substance, it's the same as another smallest unit of that substance. You know, when I pick that sample apart, it's a constant composition chemically throughout, okay? And so you can pick it apart all you want and you still have that same pure substance. So you can't physically separate it into new things, okay? Whereas the other kind of major grouping of matter that we have are mixtures, okay? And so mixtures are made up of more than one thing. And so chemically, you have multiple chemical substances in that mixture, okay? And so that is something that we can physically separate out. Now, depending on what things are mixed will determine what technique would need to be used. So sometimes it's very simple and you can like filter it through some filter paper and one substance will get trapped in the filter paper and the other one will flow through it. Whereas sometimes you have to do more complicated physical procedures, okay? Depending on what is making up your mixture, okay? But the key is if you do keep pulling apart that mixture into smaller and smaller samples, eventually you're going to get to the point where one sample's got one substance and another sample's got a different substance, okay? Even though they all started out together. Now, we can break these down even further. So pure substances can be simply elements. So all of the stuff that we have on the periodic table, okay? And so those, that is the simplest thing that you could have, the simplest pure substance you can have. You can't separate it into different things by some sort of physical or even a chemical method. So you can't take that element and do a chemical reaction that breaks it down into smaller things, okay? Now you could do a nuclear reaction, but we're not talking about that because that's a really specialized thing, okay? Now, another type of pure substance we have is a little more complicated. You can have compounds, okay? So compounds are made up of more than one element, okay? So you can have just an element or you can have multiple elements kind of bound together in a certain way, and that's a compound. But those individual units would still be constant. So it would still be a pure substance as you're pulling those individual units apart, okay, physically. But you could perform a chemical reaction with a compound that breaks it down into its elements. Okay, so you could break down a compound into simpler things, specifically atoms of elements. Okay, now mixtures, we also can kind of break down and kind of categorize a little more specifically. You can have homogeneous mixtures, and so those are mixtures that really generally look like one thing. So they can kind of trick you. A homogeneous mixture, just by sight, just visually looking at it, it's going to look like it's a pure substance, okay? So something like salt water. You look at it and it looks like water. And so that's something that visually is going to look like a pure substance, although it is a mixture. Now, since it is a mixture, you can physically separate it. So either by some sort of filtration or distillation or something that is not doing a chemical reaction, you could separate it into its individual components. And those could be either elements that are mixed together or compounds that are mixed together, but those things in that mixture are not bonded together. They're just in the same space, okay? And then you can also have heterogeneous mixtures. So heterogeneous mixtures, you have these different things mixed together all in the same space, and visually it's going to be very clear that it's multiple things mixed together, okay? And so with your homogeneous mixture and heterogeneous mixture, you know, you can kind of distinguish them visually. Homogeneous, it's going to look like one thing. Heterogeneous, it's going to look like more than one thing, okay? But also, if you just took individual samples of those mixtures, the homogeneous one, if you take multiple samples of that heterogeneous mixture, the composition should stay constant. It still has the same proportions of things, okay? Whereas a heterogeneous mixture, all of those different, you know, components that are in it are going to be dispersed differently. Okay, so there might be one portion of that sample that has more of substance A than substance B. Okay, so it may not be mixed uniformly, and that is usually part of how we can visually see that. And so those are kind of your differences. Now you can also not only physically separate a mixture, you could also do chemical reactions with those and not only, you know, separate out the substances, but break the bonds in them. Usually when we're separating mixtures, we would do physical because we don't want to make it overly complicated. Now I do have some examples of these different things. So elements can be things like carbon, mercury. Those are things that you see on the periodic table, right? So anything, you could pick anything off the periodic table. All of those things are elements. And when you have samples of those things, all the little pieces that make it up are the same, okay? Now with some elements, it'll be individual atoms. With some, those atoms are bonded to other atoms of the same element. But no matter what, as you pull that apart, you still have the same element, always, okay? And then compounds, we can have things like water, that's a compound, or sodium chloride, that's a compound, okay? Those have a constant chemical composition throughout. They're just more complicated than elements. So water is made up of H2O molecules. And so of hydrogen and oxygen, each individual molecule contains 2 hydrogen atoms and 1 oxygen atom. Okay, so as you pull apart your sample of water, you're going to get individual water molecules. Okay, if you just do physical separation of that, it's still just going to be water molecules, but you could do a chemical reaction and break it into hydrogen and oxygen. Okay, and that would be breaking it down into then its elements. And then we can have things like sodium chloride. So that's just another one that's made up of sodium and chlorine in a 1-to-1 ratio for the individual units. Okay, and so if you just have a sample of sodium chloride and you physically take smaller samples, you still have sodium chloride. Okay, but you could do chemical reactions to where then you get pure sodium and pure chlorine. Okay, which would be breaking it down into its elements. Okay, and then we look at examples of homogeneous mixtures. Some good examples: vinegar, coffee. Those are things that visually you look at a sample of vinegar, really just looks like water. So it doesn't even look like a mixture. It just looks like this clear liquid. Okay, so a lot of times, if it weren't labeled, it just looked like water until you smell it, at least. But in reality, even though that looks like it's one thing, there's actually, it's water with molecules dissolved in there, specifically acetic acid molecules dissolved in there. And so it can be kind of deceiving. It looks like it's not a mixture, but it is. Coffee, as long as you have a good filter when you make the coffee, there's not anything clearly, floating around or settled to the bottom of it. Okay, but again, that really is also just water with stuff dissolved in it. Okay, so it is a mixture, but the composition is constant throughout. But you could use physical processes to then separate those things out from one another into the different compounds that make it up. Okay, and then those compounds you could do chemical reactions with and get elements. And then we have heterogeneous mixtures. So oil and water is a really common one. So if you try to mix some oil and water, you can shake it all you want. You shake it and it looks like there's little bubbles floating around in there, and then they slowly come together and make these bigger oil bubbles within that water because it doesn't want to mix. Okay. So even though it's all in one space, they're going to kind of segment off. And so clearly it's not, thoroughly mixed. And so it definitely doesn't have a constant composition. And it also is clearly more than one thing. Okay. Also, something just like trail mix, okay? If you take a handful of trail mix and you take a second handful of trail mix and you compare what's in your two hands, there's going to be differences, okay? There's not going to be the same number of everything, okay? It's statistically impossible. It's just not going to be the same because it's not perfectly uniform throughout that. And that's because you have, all of those particles that don't thoroughly mix. There's no reason they don't interact with each other. Okay, so that's kind of some basics of how we can classify different types of matter so that we can better understand it, better study it. Okay, now there's lots of ways we can represent matter. I'm going to talk about two kind of major ways that we can represent matter. One way is to just do it in kind of a handwritten way or typed, I guess. And so if we want to handwrite or type different types of matter, we would represent it as, chemical formulas or element symbols. Okay, now you can also do names. I guess I could say that. You can name the substance, but we want to do it in kind of a shorthand way. Okay. And so in chemistry, at least, we would use element symbols and chemical formulas. And sometimes when we're talking about that stuff, yes, we will convert it to a name because it's easier, it flows better to just say the name instead of trying to, say H2SO4. We would say sulfuric acid. It just comes out quick. Okay. But you should be familiar with these different kind of shorthand representations of matter. So element symbols, I already talked about. Those are the things on the periodic table. So those are just kind of shorthand notations for elements. And you should be able to jump between those element symbols and names because that happens a lot in chemistry. Okay. And then chemical formulas, that's going to represent molecules or formula units, if you want to get really technical for some things. Of compounds. Okay, so the element symbols are representing elements, chemical formulas are representing compounds. Okay, and so the chemical formulas are always going to be a combination of multiple element symbols. Okay, and so you notice for water we have H and O, so the H is for hydrogen, the O is for oxygen, and for carbon dioxide we have C and we have O, so C is for carbon, O is for oxygen, and so on. So you always have multiple element symbols in a chemical formula. You can also have numbers. Those numbers would be subscripted, and those subscripted numbers are telling us how many atoms of an element are in that compound. Okay, now the symbols that don't have a subscripted number really are a 1. Okay, we don't put the 1s. So H2O is really H2O1. Okay, you just don't put the 1. Okay? It's assumed to be 1 if it's not there. Okay, and so that's telling you how many atoms of each element are in a molecule of that substance. So a molecule of water has 2 hydrogens and 1 oxygen in a molecule. And a carbon dioxide molecule is 1 carbon atom, 2 oxygen atoms. Okay, and so on. And so that's a very typical way in chemistry that we represent matter. Now, sometimes it is beneficial to represent things in a little more visual way. Okay, so if you're trying to understand the structures a bit better, and the reason we would want to do that is to understand kind of the bigger picture, how these things behave, we might use some pictorial representations such as ball and stick or space filling models. And so those are just helping us represent, pictorially how these atoms are bonded together. Okay, so the balls in the ball and stick are atoms and the sticks are bonds. Okay, and the different balls, a lot of times they're color coded or possibly shaded differently. The different colors or the different shadings are indicating different elements. Okay, so in that first one, you've got kind of 2 gray atoms and then 1 red one. And so though that compound, or sorry, that molecule is made up of two different elements, meaning it is a compound, okay? Whereas sometimes people will label those in the ball and stick model. So I have a couple there with phosphorus and chlorine where I've actually got the letters on there. That's not very common. Usually we just rely on the different colors or the different shadings indicating you have different elements. And sometimes you'll be given a key for what the different colors mean. But basically the idea is if you see that you have different colored atoms, you have different elements in this one molecule, okay? Now the space filling models are just kind of a condensed form, okay? And so the atoms are just kind of merged together, okay? Eliminating those bonds. And so instead of showing them, the merging of those atoms is indicating those things are bonded together. Okay, so that's it for just some basics of classifications and representations of matter.